Hello and welcome to this video lesson. This video lesson is on the reactions of amines, in particular the reactions that form amines, including the mechanisms of those reactions. So let's start off by seeing what our learning objectives are for this lesson. The first one of which is here. Okay, we want to understand that nucleophilic substitution reactions of ammonia and amines with haloalkanes form primary, secondary and tertiary amines and also quaternary ammonium salts. Yuck, what does that mean? Let's try and work out what it means. Okay, so this basically means that we're going to make amines. We're going to make amines by reacting with ammonia and haloalkanes. And when we're making it, the reaction mechanism is a nucleophilic substitution reaction. And when we make the amines, we not only make primary amines, but we make, so I'll just put 1 for primary, 2 and 3 for secondary and tertiary amines, and also quaternary ammonium salts. Okay, so that's what this one means. This rather convoluted learning objective means. We're going to make some amines by reacting ammonia and haloalkanes, but we don't just get primary amines, we get secondary, tertiary and quaternary ammonium salts as well. And while we're at it, we're going to have a look at the reaction mechanism, which is a nucleophilic substitution mechanism. That's what that learning objective means. Okay, so this one's quite a simple learning objective. So we want to know that primary aliphatic amines, so those amines with a long chain of carbons rather than a circle of carbons, they can be prepared also from haloalkanes, and which is what we've done in the first learning objective, but also by the reduction of nitriles. Right, so the second learning objective is mainly about the reduction of nitriles to make primary aliphatic amines. And lastly, we want to look at aromatic amines. So in the second learning objective there, we've made some aliphatic amines. In the third learning objective, we're going to learn how to make some aromatic amines. And we're going to do that by the reduction of nitro compounds. So there we are. There's what we're going to do. It's quite a long lesson, so let's get cracking. So in our first long convoluted learning objective, we said we were going to make some amines. So let's start off simply. Let's start off by making some amines by heating a haloalkane with excess ammonia. So excess ammonia. So let's start off with some ammonia. And we need 2 molecules of ammonia, and we're going to react that with a haloalkane. So let's say it's a bromoalkane, and let's say it's a ethane. Okay. So there's our haloalkane, bromoethane, and we're going to heat that. And what we're going to get is an amine. And we're going to study this reaction mechanism in a minute, but for now, let's just write down the amine. Okay, so we've got our carbon chain, and our bromine has been replaced by our NH2 group. So we now have an amine, but we've also got some other products. So the second ammonia molecule that we started out with takes the spare hydrogen from this NH2 group that has joined with the carbon chain. So you've got an ammonium molecule, molecular ion rather, and the bromide that was on the haloalkane. So that's the reaction that we get when we heat a haloalkane, in this case bromoethane, with excess ammonia. However, it's not as simple as that, because what happens is we get a further reaction. What you've got here is a primary amine, a primary amine here, but it doesn't necessarily stay like that, because this hydrogen here could possibly be substituted in the same way as happened as in this reaction by this part of the bromoalkane. And so what you would get is you would get another molecule like this. So you would have same but instead of the hydrogen, we've got further substitution happening. So let's just switch colour back to green, and so you've got the alkane part of your bromoalkane there, and that can happen to this hydrogen as well. But first, before we do that, let's just point out that this, of course, is a secondary alkane. So secondary amine rather. And incidentally, you would get another NH4 plus another ammonium molecule and another bromide ion, another ammonium ion rather, and another bromide ion coming off. Right, so let's go back to our further substitution, where we get the hydrogen being substituted. The remaining hydrogen that's on the NH2 group, it was an NH2 group, is also substituted in the same way. So let's draw that out. Got the original, that's that, and then we've got and so here we have a tertiary amine, where all of the hydrogens from the amine group have been substituted by the alkane part of the bromoalkane. But it doesn't just stop there. You can get a quaternary ammonium salt made as well, and I'm just going to write that in shorthand. So you've got the nitrogen, and you've got your CH3, CH2 group, but this time you've got 4 of them, and you've got, it comes with a positive charge as well. So we have now a quaternary ammonium salt. Because the substitution just doesn't just happen once to produce a primary alkane. The substitution happens again and again and again until you've got secondary, tertiary, and also quaternary ammonium salts, all in the same mixture. And so, what if you only wanted one? Let's say you only wanted the primary alkane, then you would have to separate them by fractional distillation. Anyway, to summarize, what we've done on this slide is we've shown that all different types of amines, primary, secondary, tertiary amines, as well as quaternary ammonium salts, can be produced by heating a haloalkane with excess ammonia. So we've made some amines. And what we're going to do now is look at the reaction mechanism, because it's a nucleophilic substitution reaction mechanism, and you need to know all about that mechanism, how these reactions actually happen, step by step. So as we said, the formation of amines from haloalkanes is a nucleophilic substitution reaction. So let's go through that mechanism step by step with a generic reaction. Okay, so let's start off with a generic haloalkane. So start off with a carbon, and it's got an alkyl group off one end of it and a couple of hydrogens. And it's got the generic halogen that we'll denote as an X. Now, so the first thing that's going to happen is that these electrons that are being shared in this covalent bond between the halogen and the carbon are going to be greedily grabbed by the halogen because it's more electronegative than the carbon. So we illustrate that with what's called a curly arrow, and the curly arrow is a technical term that you might see in exam questions. Okay, so a curly arrow drawn something like that, and the net effect of that that electron grab is that, of course, our halogen is going to have a little negative charge there, which we give a small Greek d, a small delta, and that's because it's grabbed it's more than its fair share of those bonding electrons, which of course leaves this carbon with a small positive charge. Okay, so this molecule is now a polar molecule. And so that polar molecule is swimming around adjacent with some ammonia molecules. And we're going to draw our ammonia like this. Of course it's NH3, you know that. I've drawn it around like that so that I can draw the spare bonding pair, or the lone pair of electrons that are still available on the nitrogen. So some of the rest of nitrogen's electrons are involved in the 3 covalent bonds with the 3 hydrogens, but its remaining 2 are a lone pair of electrons, and that's quite a dense area of negative charge, and so that's going to be attracted to the small positive charge that is present on the carbon atom of the haloalkane. And so what's going to happen now is the halogen is going to, and this happens instantaneously, the halogen takes both of the bonding electrons in its covalent bond with the carbon. It takes those electrons away with it, right? And the ammonia molecule takes the place of the halogen in that substitution reaction. And it's called a nucleophilic substitution reaction because the lone pair of the ammonia molecule is attracted to the positive charge of the carbon, which is sort of positive charges are like the charges on a nucleus. Okay, so let's just go back a step there and draw out that molecule that we're getting. Okay, so I'm actually going to do that in green over green because I want to be consistent. Okay, so I'll just repeat what I said there. We've got the ammonia molecule is swapping out for the halogen, and the halogen leaves. So the halogen's leaving with both of the bonding electrons. Okay, so it's leaving with a negative charge, which of course is going to leave the carbon with a positive charge. The rest of that molecule is the same. So we've got our alkyl group and our two hydrogens and our carbon there, and we've got a little positive remaining. Okay, well, it's a full positive, but that halogen has been swapped out by our ammonia molecule temporarily, and that positive charge transports itself over to the nitrogen because the nitrogen is quite electronegative. So the nitrogen gets that positive charge there. And this particle here, this molecule here, is called a alkyl ammonium salt. So alkyl from the alkyl group and the ammonium, because it's an ion of ammonia. But it doesn't stay like that. Obviously you can see that this is pretty unstable because our nitrogen atom in this molecule has 4 bonds. It doesn't like 4 bonds. And what's more, the electrons don't stay as they're drawn here. So let's see what happens to the electrons. So look, you've got a covalent bond here. So you've got two electrons being shared, and yet there's a positive charge on the nitrogen atom. So what happens is these electrons are drawn towards the nitrogen atom, leaving the hydrogen with a small positive charge. And guess what? There's the ammonium molecules swimming around nearby that are going to be attracted to that small positive charge on the hydrogen atom there. So you've got another ammonia with its lone pair of electrons that are very densely negative, and so that is going to be attracted to our hydrogen atom here, and that attraction combined with the fact that our nitrogen that's in our alkyl ammonium salt is not happy having 4 bonds, and so it drops off that hydrogen, this hydrogen with the small positive charge, and the ammonia molecule takes it and becomes an ammonium ion. So let's draw that in blue. So this ammonia molecule and that hydrogen atom there become an ammonium ion, and they form the ionic bond with the halide that is also swimming around to form that salt. Okay, so but how does that leave our major main molecule here? Okay, well the nitrogen is happier now because it's lost one of those hydrogens. So the nitrogen now only has 2 hydrogens like that, and it's bonded to its carbon, and the carbon still has its alkyl group and its two hydrogens bonded to it. And that is our amine, and it's a primary amine. So that's our reaction mechanism. It's a nucleophilic substitution reaction mechanism, and there are about 5 steps there that you need to be familiar with, because you could quite easily be asked to describe a reaction mechanism, and you'll need to understand the 5 steps. You won't get these exact molecules, this exact reaction, but the steps will be pretty much the same. So let's illustrate the steps. Our first step, I'm going to choose a different colour, let's say purple. So our first step is this step here, where our ammonia molecule gets attracted to the polar haloalkane. And our second step is this one up here, where the carbon can only have 4 bonds, and our halide breaks off with the 2 electrons. And our third step is going to be this one here, where our second ammonia molecule comes in. And our fourth step is this one here, where we get the hydrogen breaking off. Well, let's write this one. The fourth step is this one here. And our fifth step is the formation of our primary amine. Okay, so we've got 1, 2, 3, 4, 5 steps, and here they are in words so that you can learn them nicely. And these numbers here correspond to the steps that I've written out on the schema. So just pause the video maybe and go through each of these steps and make sure you can make sense of them. And if you can't, don't worry, because we're going to do a few examples of them. So at the risk of making the video too long and being a bit repetitive, I'm going to go through an example with real reactants making real product. So here we are, we're going to do the formation of ethylamine. We're going to make ethylamine from ammonia and bromoethane. So let's just make sure we know ethyl is going to be 2 carbons, amine, so we're going to the NH2 group there. So we'll be able to draw that if we've worked out what it's like from the name. Ammonia we know is NH3, and bromo, we know that's going to be a bromo, and ethane is going to be 2 carbons there. Okay, so now we've picked the question apart, we can draw the reaction. So let's start off with our bromoethane. So as we've worked out, we've got 2 carbons with a bromine replacing one of the hydrogens to make the bromoethane. For completeness, we'll just draw in our hydrogens. Sorry, it takes so much time when I'm drawing them like this. And as you know, the bromine is electronegative, so we get our electrons being drawn towards the bromine, which gives the bromine the polar negative and the carbon the polar positive. And that means that a nucleophile can come and attach that, attack that positive charge that's left on the carbon. And that nucleophile is, of course, the nitrogen. So, sorry, the ammonia rather, with its lone pair. In this case, it is the lone pair. In this case, it is the ammonia. All right, so that attacks the nucleus of the carbon, because the lone pair is electron dense. So that's what happens, and then what happens next is that we get our replacement of the bromide. The bromide thinks, well, hang on a minute, I can just take those both those bonding electrons, and I go off as a bromide ion. Let's draw it down here. So the bromide ion decides to go off on its own, and instead the ammonia attaches to that carbon. So let's draw our alkane just the same. But instead of the bromine, we've got our ammonia molecule. But of course the bromide has taken the negative charge, both the electrons off with it, which leaves the positive charge, which finds itself on the nitrogen atom in that bond, which of course nitrogen is quite electronegative, so it's going to draw electrons from its hydrogens. Right, so I'm drawing the electron flow in green, aren't I? So the electron come from the hydrogen towards the nitrogen to make up for the fact that it's one electron short. And what that means is that another ammonia molecule that is swimming around in the vicinity can attract this, it can go and get that hydrogen. So we've got an ammonia molecule that we're drawing like this, and that's attracted to that hydrogen, which is going to have a small positive charge because its electrons have been drawn towards the nitrogen atom in that ethyl ammonium salt. And at the same time, of course, nitrogen doesn't like having 4 bonds, and so it's quite happy to release that hydrogen and keep its electron. So the nitrogen that's in the ethyl ammonium salt keeps these 2 electrons that are in this bond, right, and becomes a neutral molecule again. And so what we get is we get NH4 plus, because these have joined together to make that NH4 plus. So now you have an NH4 plus and a bromide ion, which form an ionic bond like that. And we have to draw out our final product. And our ethane chain's just the same, except instead of a bromine on the end of it, we've now got an NH2 group on the end of it. Like that. And what I would like to point out is this word nucleophile. So this is the nucleophile ammonia molecule because it's attracted to a nucleus, attracted to a positive charge, which is just a dearth of negative charge, of course. So that is the nucleophile, and it's a nucleophile because it has that lone pair of electrons free and available, which are obviously going to be attracted to any positive charge that it comes across. So that's the nucleophile. But as it happens, if we look at our ethylamine, so let's just label this ethylamine just to be clear. That's the amine that we've produced in this reaction, but this amine group on the ethylamine has a lone pair of electrons as well, doesn't it? That has a lone pair of electrons, so that is a nucleophile as well. That is a nucleophile. This whole molecule is the nucleophile, and it's a nucleophile because, of course, as I just said, it has that lone pair of electrons available to hunt out any positive charge, that lone pair of electrons that's on the nitrogen atom. So that's a nucleophile as well, and what that means is that Let's choose a different colour. What colour can we choose? See if orange works. Instead of this ammonia molecule reacting with our bromoethane, it could have been our ethylamine instead, with its lone pair of electrons. So we could have had, let's write it like this. It could have been our ethylamine instead. That took part in that first part of this reaction mechanism. And if it was the ethylamine that acted as the nucleophile, the first nucleophile, in that first step of the reaction, then you would get a secondary amine instead of a primary amine. So ethylamine, of course, is a primary amine. And it was a primary amine because it was ammonia that first reacted with the bromoethane. But if it wasn't, if it was ethylamine that reacted with our bromoethane, it would be a secondary amine. Shall we actually do that? Let's go forward. We won't do the first step, we'll do the second step for you. Let's see if it works in brown. Okay, so we've got our, save a bit of time, I won't draw my hydrogens. So we've got our bromoethane, and as usual we get this happening to give us a positive charge for a nucleophile to be attracted to, right? But oops, let's go back to brown. We've got NH2 CH3 CH2, which is our ethylamine, but it still has its lone pair of electrons. So that's our ethylamine that we've produced in the first reaction, and that is attracted to this. And so then what we get should be in brown, really. You see how the ethylamine replaces the bromine instead of the ammonia replacing the bromine. So this whole unit here is different to the one we had in the first reaction. And so now you've got a nitrogen with two alkyl groups coming off it. But for completeness, let's just show you what happens. So one of these two hydrogens, either this one or this one, is going to be removed by a floating ammonia molecule. So in the end you get say it was the other one, then you end up with this, which is diethylamine. Should we write that down? Okay, which is a secondary amine. And I hear you asking yourselves, well, why should it stop there? Because, look, this secondary amine has still got a lone pair of electrons, so why can't it act as the nucleophile? And of course it can, right? So we're going to label that as a nucleophile as well. So that indeed could act as a nucleophile, for the first step of the reaction, in which case you would get a tertiary amine, and so on. Okay, but I haven't got space to draw that, so you'll have to take my word for it or work it out yourself. The same process, except a different nucleophile. So we can summarize that by saying that substitutions keep happening until you get a quaternary ammonium salt. So let's draw that out just to make that clear. So we're starting off with our primary amine. Let's draw that out with the nitrogen in the middle, and it's primary amine, so it's only got one alkyl group and two hydrogens, but then one of those hydrogens is going to get substituted by the alkane bit of the bromoalkane. Okay, so we have the same bit that we started with, but the alkane bit of the bromoalkane substitutes one of the hydrogens using that mechanism that we've been through in detail in the last couple of slides, and that happens again in a further substitution. So let me write my alkane in red. Okay, so then of course we get what we already had. But our third hydrogen has been replaced as well. So in this case we can say that we've got a secondary alkane here. Because in this one we've got 1, 2 groups, alkyl groups, and here we've got a tertiary alkane, sorry, a tertiary amine. Because we have 1, 2, 3 alkyl groups. But it doesn't stop there. We could also get a quaternary ammonium salt, which of course leaves us with a positive charge. That's what makes it a salt. But as well as that was the original alkyl group. These are the two ones that we've already substituted in, but we get a fourth alkyl group, and that would be called a quaternary ammonium salt. But I hear you asking yourself there, why doesn't it go further? Why can't we get a further substitution? Well, this is the answer. We've got, this is a nucleophile because we've got a lone pair. Okay, this is a nucleophile because we've got a lone pair here. This is a nucleophile as well. So we've got a lone pair. So primary, secondary and tertiary amines are all nucleophiles still because they still have their lone pair on their nitrogens. So let's write that in, nucleophiles, all three, because they all have their lone pairs available, but no lone pair here, no lone pair of electrons on the nitrogen. So that means that it is not a nucleophile. so it can't take place in any further substitutions. And so that's why it stops there. Okay, just quickly, what we're going to do is we're going to have a look back at our learning objectives, see what we've done and what we've still got to do. And our first learning objective was this. This was this convoluted learning objective. So we understand that nucleophilic substitution reactions. So we've gone through that reaction mechanism, the nucleophilic substitution reaction mechanism. And we've done that with ammonia and amines with haloalkanes. And we've formed or made all of primary, secondary, tertiary and quaternary ammonium salts. So we have now done that. Our second learning objective was this. We wanted to know that primary aliphatic amines can be prepared from haloalkanes and by the reduction of nitriles. So in this process we've done the first bit, we've done the haloalkanes preparation of primary aliphatic amines, and if you remember, the primary aliphatic amines have to be separated out by distillation, because you not only get primary ones, but you get secondary, tertiary and quaternary ammonium salts. And so we know that we can make primary aliphatic amines by reacting ammonia with haloalkanes, but also we need to know we can prepare them by the reduction of nitriles. So that's what we'll do in the next slide, before we go on to our last learning objective. Yeah, so the second way to produce aliphatic amines is to use nitriles, and to reduce nitriles. So firstly, should we check that we know what a nitrile is? So this is a compound with a carbon-nitrogen triple bond like this. That's a nitrile. So let's start off with ethane nitrile. So it's going to have 2 carbons in it because it's ethane. So we're going to have CH3C triple bond nitrogen. That is ethane nitrile. I'll just write that down. Ethane nitrile. Right, and that is reduced. And it's reduced by a very strong reducing agent, lithium aluminium hydride in dilute acid. And because it's reduced, in this case we're adding 4 hydrogens. We're adding 4 hydrogens, and what we get is ethylamine. So you've got the same CH3 group, but now you've fed a lot of hydrogens onto that triple bond. So you've got CH2 and H2, and that is called ethylamine. Alright, so there it is. Just to go over that again, you've got, start off with a nitrile, say ethyl nitrile, ethane nitrile, and you reduce that by adding hydrogen to it using a very powerful reducing agent called lithium aluminium hydride in dilute acid, and that gives you your ethylamine. Now, students in the past have struggled with that as a reduction reaction. So let's just look at all the oxidation numbers. So let's look first at ethane nitrile. Look over to the left at ethane nitrile. And of course it's a neutral compound, so the overall oxidation number is 0. But nitrogen is going to be -3, and hydrogen is going to be +3. So the 2 carbons together are going to be 0. So that's the oxidation numbers of the components of ethane nitrile. But if you look over at ethylamine, nitrogen is still going to be -3. But now look how many hydrogens we've got. 3, 4, 5, 6, 7 hydrogens are going to be 7 plus 7 for all the hydrogens. So that means the 2 carbons, these 2 carbons here, are going to be -4 together. So they've gone from 0 to -4, which is how you can say it's been reduced. And it's been reduced by adding all those hydrogens. So that's the reaction that can produce ethylamine. It's a primary amine, and it's just produced on its own, and then the reaction stops. We don't get any secondary, tertiary or other amines. And so the advantage of this reaction is that we don't then have to go and distill it off to find our primary amine. However, this is a reaction that we can do in the lab in small conditions, but lithium aluminium hydride is very expensive. So in industry they don't use lithium aluminium hydride. What they do use, we'll look at on the next slide. Yes, in industry what they use is catalytic hydrogenation. So as that name suggests, we're hydrogenizing, we're adding hydrogen gas to our nitrile, and we're doing it in the presence of a catalyst to speed up the reaction. So let's draw it out. We'll start with the same nitrile, ethane nitrile. So we've got CH3 C triple bond nitrogen, and instead of adding hydrogen atoms like we did before, the hydrogen atoms coming from the reducing agent, then we're going to add hydrogen gas. Adding hydrogen gas is much cheaper, but you need a catalyst. In this case it's a nickel catalyst. And you also need high temperature and pressure. Okay, so under those reaction conditions you get your ethylamine, and you get it a bit cheaper. So you'll need to be aware of both of those reactions to produce your primary aliphatic amine, in this case ethylamine. I will just write those names down in for you if you like. We've got ethane nitrile making ethylamine, and this method has used catalytic hydrogenation, in this case using a nickel catalyst with high temperature and pressure and hydrogen, and previously we used a reducing agent to add hydrogen atoms, and that was lithium aluminium hydride, which is expensive, so we use this instead. Otherwise you wouldn't buy the products. Okay, we'll do another quick check of our learning objectives. We've already checked that we've done the first one, and the second one we had already learned how to make primary aliphatic amines using haloalkanes, but now we've also learned that you can make the primary aliphatic amines by reducing nitriles. So we've done that one, and we can move on to our last learning objective, which is to switch from aliphatic amines to aromatic amines, and see how we can prepare aromatic amines. So like we said, aromatic amines are produced by reducing a nitro compound, such as nitrobenzene. So just to make sure that everyone's familiar with aromatic, then what we mean by that is a benzene ring, like this, and if it's an amine, of course, it's going to have an amine group hanging off the benzene ring. and they're produced by reducing a nitro compound, such as nitrobenzene. So nitrobenzene looks like this. So we've got our benzene ring. And we've got nitrogen dioxide coming off the benzene ring. And what we want to do is we want to reduce that, but it's a two-step process. So the first step is that we're going to use a tin catalyst and some concentrated hydrochloric acid, and we're going to reflux that together. And if you don't know what reflux is, it's the continual boiling and condensing of something. So that's what reflux is, and that would make a salt. And then what you do with the salt is you do the second step, which is to add some sodium hydroxide. Add some sodium hydroxide, and then you get your phenylamine. Okay, so your benzene rings like that, and instead of nitrogen dioxide, you've got the amine group there, and you've got some water being given off as well. And if you're interested in what the salt was that we produced in the first step, I'll draw that up here. So that's going to be your benzene ring, of course, and you're going to, let's draw it off this corner here. That's the salt produced in the first step by refluxing it with concentrated hydrochloric acid and tin, and then you add sodium hydroxide, and the sodium runs off with the chloride, and the hydroxide takes the extra hydrogen and makes a water molecule with it, leaving these two products here, our phenylamine and our water. So let's have a look at the equipment that we might use. Sorry, that overlaps a little bit. So have a quick look at this, and I'm going to label it as we watch. So we've got a cooling jacket here. I'm going to switch to red so that you can see it against the blue. So that's our cooling jacket. So you're going to have cold water in. And less cold water, let's call it warm, warmish, water out, and that condenses the mixture. So what you're going to do is you're going to heat this, and in here you have your, this is where you have your reaction, your first reaction. So you've got your tin, you've got your concentrated hydrochloric acid, and you've got your nitro compound like nitrobenzene. And that's where you do your reduction, which reminds me we need to add our 4 hydrogen atoms, which we draw like this, just to distinguish them from H2 hydrogen gas. So what we want to do in the end is replace the 2 oxygens. Let's switch to red. We're going to replace these 2 oxygens with hydrogen, and that's the reduction process to get our amine. But what we have to do is we have to go through 2 steps. We make a salt first, where we add the hydrogens, but we also add the chlorides, and then in the second step we extract the chloride and one of the hydrogens to leave the amine group. So this is the first step, what's going on in the beaker, all right, and you're heating it so it's evaporating and the gas is coming off here, and then it's condensing in your cooling jacket, and then it's coming back down, and that's happening continually, and that helps the reaction proceed. And then once you've done that for a while, you're going to add your sodium hydroxide, and this is your sodium hydroxide here. That's your sodium hydroxide that you can add into the reaction mixture. And that's how you would do it if you were doing it in a school lab. So lastly, let's just check we've dealt with all our learning objectives. We've already checked the first two, and let's see if we now know that aromatic amines are prepared by the reduction of nitro compounds. So let's just break down this word reduction. What we did was we started with nitrobenzene, and that had NO2, and we ended up with our amine, so we had NH2. So in that process we replaced the oxygen with our hydrogen, so that's how we can call it reduction. And so we've reduced a nitro compound, and as we've said, we start with nitrobenzene. So I think we're justified in ticking that last one off as well. So thank you for staying with me through that quite tricky mechanism, and I hope you've understood it nicely, but in any case we'll get some practice.